Next, let's talk about the decoders. So what are the decoders? Decoders are digital circuit that detects the presence of a specified combination of bits at the input, okay, and indicates the presence of that code by specified output level. So basically what does mean is, for example, if you use the, like this one, the binary decoder, so let me open it here, okay, so this is the example of the decoder here. Second. Okay, so you can see the decoder here. So we have the 4-bit sequence, and from this 4-bit sequence we want to know the decimal value of this 4-bit sequence. So if, for example, if the input is 000, then we know that the decimal value for the 000 is 0 here, right? So in this case, output 0 of the decoder will go high. So this decoder has, if you have the n-bit input, so in this case the n is equal to 4. For the 4-bit input, you have the 2 power of n. In this case, the 16-bit output. Sorry, the 16 outputs, right? So these are the 16 outputs. So in this case, if, for example, A is 000, the output 0 will go high. If, for example, let's say the input is 0001, so this means the decimal 1. In this case, as you can see, the output 1 is going high here, right? So we can change. For example, let's say that we have the 0101. So 0101 indicates the 5, so meaning the decimal 5. In this case, this is decimal 5, and as you can see, the output 5 is going high. Okay, so this is the simple function of the decoder. Whenever you have the binary input, it can convert it to the decimal output. This is one of the functions of the decoder. So as we said, the decoders can have the n-bit input and 2 power of n outputs. Okay, let's go back to our slide. Right. Now, how we can actually do this is as you can see, this is already the fixed function logic. You can use this, but how is it implemented? I mean, using the logic gates, very simple. So we just refer to the truth table. So this is a truth table for this 4-bit decoder, right? And these are the inputs 0000 until the 1111. All we have to do, we just create the circuit for each of these inputs. So this is, for example, this is the expression that can indicate the output when the output is equal to 0, right? So by just using these expressions here for each output, we can actually create this kind of the circuits, or this kind of circuits for each output. So in this case, this output indicates when the input is equal to what? The 1. Sorry, we read from here. So 1 0 1 1. Okay, so 1 0 1 1. So when the input is 1 0 1 1, the x will be equal to 1. So this is just the single output. Okay. And you have for example, for the 4-bit, you have the 16 outputs. So meaning you have to create the 16 circuits like this one, similar to this one. Of course, the different circuits will have the different loop. Like, for example, here. So this is for example, this is the circuit to indicate when the input is equal to 1001. So meaning that if you want to create this decoder manually using the logic gates, you have to create the 16 circuits. 16 circuits for each of these Boolean expressions. Okay. And these are some existing fixed function logic devices. You can just refer to your lecture materials. And this is just basically this, for example, this one here is the same as this implementation here inside the circuitverse. Okay, so whenever you change the input, different output will go high. Okay, so you can see that this is 0111, so output 7 is going high. Okay, so this is just a demo of that fixed function logic device. Also, for the decoders, we can use this is in case of the BCD. If you remember the BCD, the binary coded decimal, only difference from the previous decoder is that in case of the BCD, we have the limited number of outputs, only from the 0 up to the 9, right? So if you remember about the BCD, so in BCD, we have some invalid numbers, so we just ignore that invalid numbers and we create the decoder just for the 10 outputs from 0 to 9. And this is the truth table. So you can actually create the decoder just by looking at this truth table here. And this is how you're going to read the output of the decoder for the binary, the waveform input. So in this case, we have the digital waveforms, right? So to read the digital waveform, we have to focus on the single clock cycle. For example, let's say that we focus on this clock cycle here. So I don't know, for example, this clock cycle. Let's refer to this clock cycle here. Okay, so in this case, so A0 is 0, right? And then 1, 1, 0. So A is equal to, so we read this is the most significant bit, so 0, 1, 1, 0. So 0, 1, 1, 0, we know that it's equal to decimal 6, right? So this is a decimal 6. So in this case, the output 6 have to go high. But in this case, if you look below, that they implemented the reverse logic, so that means the output 6 is going low in this case. So if you go here, the below, so this is the output 6, it's going low, okay? All the other outputs are going high here, right? So this is high, 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 okay? And only this single output is going low. And you can do this for other, for example, here at this clock cycle, let's read the value of the A. A is equal to, for example, 0, 1, 0, 0. So which means the A is equal to 0, 0, 1, 0. And 0, 0, 1, 0 is equal to decimal 2. So if you look here, the decimal 2 here, right? So this decimal 2, so this output is going low. All the outputs are going high. Okay, so all the outputs are going high. So this is how you're going to read the relation between the input and output of the decoder when the input is in a digital waveform. Okay.